When a massive body collides against a, so this is M1. Shita? I think so. I have to. Okay, when a massive body collides against a light stationary
Can
body.
you just show the previous slide onward, please?
So, the first one, we finished this. This one, right?
Yes, thank you.
Now, when a massive body collides with a lighter one, so this is M2. So U2 is equal to 0.
Ma'am,
This is, yes?
this is fourth one, right? Fourth case.
Okay. So M1, M2. So M2 was initially at rest. So in that case, M1 is very much greater than M2. So in equation V1 and V2, you neglect M2. You neglect M2 and just use only M1. Will you be able to find, boss?
Yes, ma'am, one second.
Ma'am, is B2 equals to U1?
V2 is equal to U1?
U1.
Okay. 2U1, right? Yes. M2 is you're neglecting M2, right? Are you getting these values, boss?
Yes, ma'am. One second, ma'am.
Okay.
Ma'am, this derivation is called elastic collision in one dimension.
Yes.
Yes, ma'am.
So you know how to write the statement. When a massive body collides against a light body at rest, the velocity of the massive body remains almost unchanged, but the light body starts moving with twice the velocity of the massive one. Right? This is how you have to do this. Statement, you can write it in your own words. Shall I go for the other one? Boys, have you completed?
1 minute, ma'am. 1 minute.
Okay.
When you mean by one-dimensional,
One-dimensional means moving
head
along
is-
either x-axis or y-axis or z-axis. One dimension.
okay,
If it
so
moves in
the
a
collision
plane,
is straight, linear, basically.
linear, yes.
Uh,
Now we'll go for 2 dimensions also. Elastic collision
one-
in 2 dimensions. Okay, fine.
Oh, yes, ma'am.
Now we'll go for inelastic collision in 1 dimension. Just now we saw elastic collision in 1 dimension. Now inelastic collision in 1 dimension. So inelastic collision, in that sense, your momentum will be conserved, but kinetic energy will not be conserved. Now, actually, this is sometimes we call this as perfectly inelastic collision. Under inelastic collision, you're going for perfectly inelastic collision. Now, what is going to happen is when 2 bodies collide with each other, after collision, both the bodies will stick as one body and move. And this is what we call it as perfectly inelastic collision. So in inelastic collision, momentum will be conserved, but kinetic energy will not be conserved. And a special case of inelastic collision is when 2 bodies collide with each other, after collision, if both the bodies stick together and move, then it is called perfectly inelastic collision. Right, boys?
so after sticking, both the velocities will be same, right? Because
Yeah, both the it moves with the same velocity. So first, initially, if it is moving with u1, this is u2. Finally, both will move with velocity. This is m1, m2. So this will be m1 plus m2 together. Diagram, you can draw the diagram, a rough diagram. You can just write before collision, after collision. So in inelastic collision, momentum is conserved, but kinetic energy is not conserved. Kinetic energy is not conserved.
Ma'am, should we write this?
Yes, you have to write, boys. In elastic collision, momentum is conserved, kinetic is not conserved, kinetic energy. Perfectly inelastic collision is that after collision, both the bodies will stick together and move with a common velocity as a single body and move with a common velocity.
So for this, there'll be only one V.
It will be one way, yes. Final velocity is just V. It's completed.
1 second.
Ma'am,
What happened?
ma'am,
This is
ma'am, should you draw the diagram? Like
diagram
the...
is a rough diagram. You draw a rough diagram. Boss.
Okay, ma'am.
Have you completed, boss?
Yes, ma'am. Yeah.
Now, in such collision, what you have to prove is that when two bodies collide with each other inelastically, after collision, if they combine and move with a common velocity, what you need to now prove is that the change in kinetic energy should be positive. This is the first one you have to prove, and you have to prove that your initial kinetic energy is greater than final kinetic energy, because there is a difference in kinetic energy, and this shows there is a loss in kinetic energy. So two things you have to prove. One is you have to prove that your change in kinetic energy is a positive quantity. The second one you have to prove initially the body is moving with the total initial kinetic energy must be greater than the final kinetic energy. In that sense, there is some amount of energy is being lost. So these two things we need to prove. Initialization, you always have to write. So what is that you are having? Only thing is that what will, I think so, was in the previous case, I think in this diagram, we'll take U2 as 0. Right, boss? We are taking a special case. We are considering U2 is 0. It's at rest. Okay. Consider a body of mass m1 moving with a velocity u1 collides head-on with another body of mass m2 at rest. So after collision, both the bodies will move with a common velocity v. Okay. Now, linear momentum is conserved. If linear momentum is conserved means what? Total momentum before collision must be equal to total momentum after collision. Total momentum before collision must be equal to total momentum after collision. So what is m1 u1? It is the momentum of the first body. m2 u2, that is u2 is 0. This is the momentum of the second body. So that must be equal to final momentum. This equation is total initial momentum must be equal to final momentum. So then you find the value of V. Total
What happens to
initial.
U1 in the final equation?
Sorry. U1. So total initial momentum must be equal to final momentum. So you have two bodies. The first one is moving with a velocity u1. The second one is having a velocity 0. Then two bodies stick together and move with a common velocity v. So now you get an expression for v. V is equal to m1 plus m2 by m1 into u1. So you have got an expression for v. Now, the next step is, what you do is find total initial kinetic energy. Total initial kinetic energy. That is, you have to, both the bodies, find their total initial kinetic energy So that is Ki.
Ma'am,
Yeah.
is the expression correct? The last one.
Yes,
Yeah,
ma'am. Shouldn't be the
but-
reciprocal of it.
sorry. Yes, I think so. Yeah, okay, V is equal to M1 by M1 plus M2. Sorry, into U1. Correct. Sorry. Are you getting this?
Yes, ma'am.
Now find total initial kinetic energy. So total initial kinetic energy will be kinetic energy of the first body plus kinetic energy of the second body before collision. Total initial kinetic energy before collision. So let it be Ki. Then you can write kinetic energy after collision. That is Kf. Then you can find change in kinetic energy. So these three steps you have to find. So right, what will be the total kinetic energy before collision was?
Half mu1 square.
Okay, half m1 u1 square. The second one is 0 because the second body was initially at rest.
Yes, ma'am.
Others? 11b?
Yes, ma'am.
Yes, ma'am.
That's fine. Rishit? Rishit? Okay, Rishit is Derek and Danish. Derek?
Yes, ma'am.
Is that fine? You know why the total kinetic energy is half m1 u1 squared plus 0?
Yes,
Should
ma'am.
I do? No, if you don't understand, I'll redo this. Should I redo?
It's fine.
So what is kinetic energy after collision? Sorry, I think so. I'm speaking to Derek. Yeah, or Danish. Okay. What is the mass of the bodies after collision? The two bodies combine with each other. So what will be the total mass? M1 plus M2. Then what is the velocity? V squared. Is that fine? Now
Yes,
you
ma'am.
find the total change, so the change in kinetic energy. So it will be Ki minus Kf.
Ma'am, it should be
Ki
KF
minus
Ki,
Kf
right?
or Kf minus Ki.
Ki minus Kf.
Okay, ma'am.
So if I so it will be half m1 u1 squared Are you able to complete these things, boys? Are you able to complete?
Yes, ma'am.
Now what you do is take the common factor over here, which is common. Half is common, m1 is common, u1 squared is common. So here half is common, only m1 is common, then u1 squared is common. Take the highlighted part outside the brackets. Shall I go for the next one? Or shall I go for the next one?
Yes, ma'am.
Yes, ma'am.
Right? So then I have taken the common term outside. Now take the LCM. So what you are getting is a positive quantity. So this shows that the kinetic energy is
Ma'am?
lost by this. What happened?
Ma'am, did you change the slide?
I want to copy now.
Oh, no, ma'am.
Can
Like,
go
did you
to the
change?
next slide?
Yeah,
Because for us it's stuck. So that's
Same slide, ma'am, for us.
same one.
No, we are in the one in which
change
you
in
highlighted
kinetic
half
energy.
m1 u1 square to take
Ma'am,
out.
can you change the slide? I
Uh,
think it's stuck.
Are you in the loss in kinetic energy on collision?
Yes, ma'am.
Yes, ma'am.
Okay. Now you can't- Next one, delta K.
We can't
The
see it.
We can't
next
see
slide
it.
is not visible.
No,
Okay, one
it's stuck.
second.
Can you reshare?
Is it fine now? Can you see?
Yes, ma'am.
The delta K, that is, I've just written this is a positive quantity. Can you see that?
Yes, ma'am.
Next task is yours, right? So you have to prove Ki is greater than Kf. So you have the value of Ki. K is the total kinetic energy before collision. Kf is the kinetic energy after collision. Just prove, you'll be able to prove this Ki is greater than Kf. Just get me an expression for what is the expression for Ki by Kf. Then we'll see how to argue. Okay, someone tell me what is an expression for Ki? What is the expression for Ki? Half m1 u1 squared plus the second body was at rest. I'll put 0. What is Kf? Half m1 plus m2 into v squared. This half and half will get cancelled. So what is the value of v squared? Can you substitute for, so Ki by Kf will be equal to m1 u1 squared divided by m1 plus m2 into v squared. Now you have to substitute for v.
Oh, ma'am. Ma'am, what's that? In the conclusion statement,
Hmm.
this is a positive.
Yeah,
What's after
this is
positive?
positive quantity, sorry, positive quantity. Abbreviated. Now you have to substitute the value of, v squared, v over here. Boss, I'm just making you people to do. Are you able to do, or should I continue doing?
No,
Or solving? You can do. Okay. So you have got an expression for V. Substitute the expression for V.
Ma'am, is it M1 plus M2 by M1?
Yeah. M1 U1 squared by.
Ma'am, why are we proving that Ki is greater than Kf?
Because see, in elastic collision, energy is lost. If energy is lost, initially, if you have 50 joules of energy, finally after collision, if you have 20 joules of energy, 30 joules of energy is lost, right? That is how you prove.
All right, ma'am.
Now you substitute, boys. How many of you have completed substituting for V?
Yeah, yes, ma'am. Still working on it.
Okay.
Ma'am, I'm getting a ratio U1:1.
Yeah, I'll do that. So shall we move for the next one? Or shall I substitute and let us see what is happening? Fine. Now, if I go for it, sorry, I'll take a new slide. Okay, if I go for the new slide, I have so Ki by Kf is equal to M1 U1 squared divided by M1 plus M2, correct, into M1 squared by M1 because it is V squared, M1 plus M2 the whole square into U1 squared. This is what I am substituting for V squared. So this M1 will get cancelled. This and this will get cancelled. So what I'm left is Ki by Kf must be equal to M1 plus M2 divided by M1 because this is denominator. Now Ki must be equal to M1 plus M2 divided by M1 into Kf. Suppose if I give a value, if you want to check, say if I give the value of M1 as 2 kilograms, M2 as 1 kilogram, then what is this value comes to be? 2 plus 1 by 2. So 3 by 2, that is greater than 1.5. Sorry, greater than 1. Yeah.
Yeah, greater than 1.
1. So if you want to argue, you can go for that. That is why Ki is greater than Kf. Ki will be greater than Kf. You can just give any values. Randomly, you can give a value. You can have M1 as 3 kilogram, M2 as 2 kilograms. There also you can check. So you can prove that Ki is greater than Kf. So the last topic, what is left is elastic collision in 2 dimensions. So we started with elastic collision in 1 dimension. Then we went on to inelastic collision in 1 dimension. Next is elastic collision in 2 dimensions. So before going for the derivation, I thought I'll go for a numerical, then it would be easy for you. So Ki will be greater than Kf.
Ma'am,
Yes,
remember in this case, the U2 is equal to 0, right?
U2 is 0, correct.
Okay.
Now you're only substituting for the, so here this quantity will be 0.
Okay.
One textbook numerical on conservation of mechanical energy, we'll do this numerical. Once you have completed, so Ki is greater than Kf. So what you can say that, and if Ki is greater than Kf, it proves that energy is lost after collision.
Yes, ma'am. Ma'am, can you post a revision paper for work energy and power for the coming test?
Coming test revision. No, revision
Yes,
will be next week. Next entire week will be for revision.
Okay, thank you.
That's what. So let me complete. Only one more topic is there. I think that will take a long time. Just the last topic. Before that, I'll just go for a numerical. I think I have enough time for going for a numerical.
4 minutes.
Okay, I think so. I can go for it. Shall I go for the next one slide, boys?
Yes, ma'am.
Yes, ma'am.
Just I'll draw the diagram. You just think whether you people can do this numerical, right? It is based on conservation of energy, mechanical energy, that is kinetic and potential. The total energy remains a constant. Now look at this. You have a simple pendulum, right? Now this is going to, the pendulum is oscillating. So now the pendulum was initially at this position A, right? The length of the pendulum is 1.5 meters. Now this is this level is taken to be the ground level. Say I can say from the center of the ball. This will be your reference level. See, you have a pendulum. Must keep this in mind. When the pendulum is oscillating, if there is no air friction, and the pendulum keeps oscillating when there is no air friction. Now at the extreme position, which are the extreme position? These are the extreme position. At extreme position, the energy is only potential, kinetic is 0. Same way here also. At the extreme position, energy is totally potential, kinetic is 0. But at the mean position, this is called the rest position. At rest position, the energy is totally kinetic, potential is 0. But when it is moving from, say, from the extreme position to the rest position, here potential will be converted to kinetic. Is that clear, boys? When you have a simple pendulum, at the extreme positions, the energy is totally potential, kinetic will be 0. Now, at the mean position, when the pendulum is oscillating, when it comes to the rest position, the energy is totally kinetic, potential will be 0 because this is taken as the reference level. So this, you have to keep this in mind, boys. Right? Only this you should know in a simple pendulum, when there is no air friction, total mechanical energy is conserved. At the extreme points, potential energy is totally potential at the extreme positions. At the mean position, this is the mean position. At mean position, the energy is totally kinetic. Now the question is, when the metallic bob reaches the point B, it dissipates 5% of its initial energy against air resistance. So when the bob reaches point B at the lowermost point, at the lowermost point B, the Bob dissipates 5% of its initial energy. What might be its initial energy, boys? Look at this. This is the initial position. What is the initial energy? What will be the initial energy? I told you this is the extreme position. You know what is the extreme?
Potential energy.
Potential
Ma'am,
energy.
Islamic
Yeah.
class started.
Okay. You can leave.
Thank you, ma'am.
Thank you.
Thank you.
Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, boss.
Thank you, ma'am.
Thank you.
Thank you.